Hey there, folks. This is Mr. Young, and I'm going to take you through a quick lesson on the idea of entropy. Entropy is a measure of the disorder or chaos in a system. Okay, so entropy equals disorder. All right. If you just think of something like some paper burning, okay, a sheet of paper is mostly made of cellulose, and combustion means that that fuel is combined with oxygen. And when you burn something or combust something, the two main products are carbon dioxide and water vapor. Okay, so we take a piece of paper and we ignite it, and let's think about the disorder. Okay, we start out with this nice, neat, organized piece of paper, and we end up with these two different gases that are being produced and spread all around the room. And maybe we end up with some ash as well. So we start out with a system that is more organized. Okay, we got that nice cellulose in that piece of paper and some oxygen gas nearby. When it goes through combustion, we end up with two different gases that float away. And maybe we even end up with some leftover ash. So that is more disorganized afterwards. So we say it has higher entropy. We start out with less entropy in this reaction, and we end up with more entropy or higher entropy. So this reaction represents an increase in the entropy of the system. We go from low entropy to higher entropy. And in general, the universe naturally moves towards more entropy or higher entropy. Okay, something like an egg is pretty organized. It's got lower entropy, but most eggs eventually are going to end up broken in some way, and nature will tend to move towards higher entropy or more disorder. Unless you do a lot of work to try and keep things organized, nature will tend to move towards higher entropy. Think of something like a forest. The trees in a forest are eventually going to die and fall down and rot and decompose, and their molecules are going to be turned into new organisms. So a forest is pretty organized. It has low entropy, and eventually it is going to move to a situation where it has higher entropy. That's just natural. The universe naturally moves towards more entropy. You even saw this, excuse me, in earth science. Um, if you have erosion and weathering happening, well, the soil packed in a cliff is pretty organized compared to the soil particles that wash away into the seawater. So nature naturally moves from the organized soil packed into the cliff to the soil that is washed away and carried away and mixed into the seawater. So nature naturally moves towards higher entropy. That's just what happens in our universe. We can even think of phases in terms of entropy. Imagine ice cubes melting into water. Okay, those particles start out more organized, end up a little less organized, so they move from lower entropy to higher entropy. Remember, higher entropy means more disorder. If we turn that water into steam, it's got even more disorder. Those particles are moving around more, they're more disorganized than the liquid. So if we think about gases, solids, and liquids, we can arrange them by their amount of entropy. Remember, entropy is disorder. And when we're thinking about particles and phases, entropy depends on the positioning and the motion of the particles. So if we tried to classify these from least entropy to more entropy, as we said, solids have the least entropy, liquids have a little more entropy, and gases have the most entropy of all. They're the most disorganized. Now, what about that other? It's not quite a phase, but often in chemistry, we're talking about aqueous solutions. So, an aqueous solution, you have a liquid and you've got a solid that is dissolved in it, like these sodium and chloride ions that are dissolved in H2O. Where would that fit on this scale of least entropy to most entropy? Well, it's going to be more disorganized than a liquid, but not quite like a gas. So it's like you've got a liquid with extra particles dissolved in it. That makes it have more entropy in terms of its classification than a liquid. So it fits between liquid and gas. Okay. So remember, entropy is a measure of disorder in a system, and nature moves towards disorder. Nature prefers disorder. Entropy can be also thought of as chaos, if you like that word a little better. Okay, now we can increase entropy in three different ways. You can change the phase. Okay, so if we think of from low entropy to high entropy, solids have the least, liquids have the middle amount, gases have the most entropy. Aqueous solutions are between liquid and gas. So there's just a full scale going from low entropy to high entropy. If we increase the temperature, then there's more kinetic energy, then there's more particle motion. That will also increase the entropy. Okay. And then if we also have more particles or more moles of a substance, then it will have more entropy. There's more stuff, there's more particles moving around, so that would be more entropy. So we're going to analyze a couple of different chemical reactions or processes in terms of their entropy. Are they losing or gaining entropy overall? The way you do this is you just think of that scale. Solids have the least, then liquids, gases have the most, and aqueous solutions are in between liquids and gases. So to analyze these, all we do is focus on the phase, okay? So in this reaction, we start out with solid aluminum and oxygen gas, and at the end, we've produced a solid, Al2O3. Overall, we go from a solid and a gas to a solid. We're going from more entropy to less entropy. So entropy overall decreased. They were more disorganized, and now they're more organized in terms of the phases and what has more and less entropy. In reaction B, we've got solid copper and an aqueous solution of HNO3. And at the end of this reaction, we've got an aqueous solution, a gas, and a liquid. So we started out with a solid and aqueous solution. We end up with an aqueous solution, a gas, and a liquid. So overall, you can see that entropy increased. If we kind of add up the entropy of these things, they have more than what we started with. Or you could just say, okay, the AQ cancels out. You have a solid switching over to a gas and liquid. If the AQ cancels out, the gas and a liquid have more entropy than a solid. In this third one, this is a little tricky. We start out with a gas and another gas, and we end up with a gas. So it goes from gas to gas. Well, entropy, I guess, doesn't change. Nope, that's not the case. Think about these coefficients that are in front. We have 1 mole of nitrogen gas and 3 moles of hydrogen gas. But at the end, we only have 2 moles of NH3 because of the way that the atoms and molecules recombine. So we start out with more moles or more particles of gas. We end up with less moles or less overall particles of gas because the atoms and molecules have combined themselves together. So in this case, entropy has decreased. We started out with more moles or more particles, ended up with less moles, less particles, and you use this technique if you've got something where you got the same phase on either side of the equation. One more thing to help you kind of remember about entropy and our universe. Systems in nature prefer high entropy, that's disorder, and low energy. We'll be talking a lot about potential energy in this unit. So if you think of a teenager's bedroom, that'll help you remember what the universe likes. Nature or chemical systems want to be like a teenage bedroom. Classically, in the cliche, a teenager's bedroom is supposed to be messy and disorganized. That represents high entropy. And here we see the teenager sleeping on a mattress on the floor. Things that have low energy are very stable. The universe wants to move towards a low energy situation because it's more stable. But the universe also likes disorganization and high entropy. So systems in nature prefer high entropy and low energy. Low energy is more stable, and disorder is natural. Okay, a couple more practice questions. Given the equation KNO3 solid dissolved in water to make KNO3 aqueous, if water is added to KNO3 solid to form KNO3 aqueous, the entropy of the system. Okay, to analyze this, you just think of the phases. You start out with a solid, you end up with an aqueous solution, and so overall we're going from something with less entropy to more entropy, so entropy increases in this case. Systems in nature tend to undergo changes towards, think of the teenage bedroom, towards lower energy, the mattress on the floor, and higher entropy, the messy bedroom. Which phase change represents a decrease in entropy? Okay, you got to think of the scale from low entropy to high entropy, and going from gas to liquid would be going from higher entropy to lower entropy. One more practice question. Which of these changes produces the greatest increase in entropy? Greatest increase in entropy. I bet you 3 of them are going to be a decrease and 1 of them will be an increase. That's usually how this works. All right, we've got a solid becoming a solid and a gas. We've got a solid and a gas switching over to a solid. We've got a gas becoming a liquid and a gas becoming a solid. So we can rule out number 4, gas becoming a solid is a decrease in entropy. We can rule out number 3, gas becoming a liquid is a decrease in entropy. We can even rule out number 2. We've got a solid and a gas on the left and just a solid on the right. That's again a decrease in entropy. So, but number 1, a solid becoming a solid and a gas, that is an increase in entropy. On the left we have just a solid, on the right we have a solid and a gas. That's got more entropy overall. Okay, that's it for this lesson on entropy. Thanks for watching.